Introduction to exercise 9.1 on the natural exponential function y equals to e to the power of x. We're focusing on this Euler's number. Of course, e we're using Euler's. Euler's number is a special irrational number which we introduced in this topic. It's very similar to pi, in which case it's a special number for a particular reason, but it never ends. Okay? Now, mathematically, it's derived from this. E is equal to the limit of n moving towards infinity, or approaching infinity, of 1 plus 1 over n to the power of n. Right, and we approximate it, you will never need to memorize this. You probably need to know that E is about 2.71 or 2.72, right? But you don't need to memorize it. Anytime you're using E in exam 1, you keep it as a E, right? Anytime you do it in exam 2, you've obviously got a calculator, okay? So you'll never need to find the exact value, of course. Oh, sorry, the rounded value. We use e as the natural base for exponential and logarithmic functions. We'll talk a little bit later about why it's so special, but for now, just accept that it is, and let's move on. The graph of the exponential function, as I mentioned earlier, has two key properties. Of course, it has a horizontal asymptote at the x-axis, and a y-intercept of 1 and no x-intercept. Of course, it won't make sense if you try to put in let y equal to 0. Right? Because you end up with like -3 equals to 3, which obviously doesn't make sense. Transformations can be applied to exponential functions as any other function as well. I'm going to just give you one example and we'll leave it there. Sketch the graph of f of x equals to e to the power of x plus 1 minus 2, showing the coordinates of y-intercepts. This is exactly the kind of question where if you're stuck in an exam or an assessment with a calculator and you're not sure how to graph it or you're not sure how the value would change, you can use a slider to see how that would change. Of course, in this circumstance, it seems very clearly it's just a transformation, specifically translation. If I was to write it out, I could write out that it goes towards an f of x plus 1 minus 2, or really if I wanted to separate it out, I could write going towards f of x plus 1 and then minus 2. Okay, so of course we're applying our translation. Our transformations apply the same way, right? Of course, instead of being in a bracket, like for example our quadratic functions, we're just focusing on the power and with values on the outside as well. E, again, is just like any other number, 2.7. We just treat it as e. So if we're going to sketch the graph of e to the power of x plus 1 minus 2, I'm going to go ahead and sketch my original function. Now you don't need to do this step. I'm going to go ahead and show you what e to the power of x would look like. It's pretty crazy. It looks like an exponential function, right? Obviously, if I put in an e to the power of x, y equals e to the power of x, right? And of course, I would substitute a value of x equals 0, end up with e to the power of 0, which is of course 1, and we still end up with 0, 1. Let's see what happens if we apply our translations. Of course, it's x plus 1, we're translating left. When I move right, left 1 unit, of course, and 2 down. Our x-intercept, so not x-intercept, our asymptote equation, which originally was y equals 0, is going to get shifted down to y equals to -2. So I'm going to go ahead and do my dotted line there. I'm going to do this in a different color actually. Y equals to -2. Alright, of course, and then we end up with, of course, a translation 1 to the left. So our function should look something like this. Hopefully yours has a bit nicer asymptotic behavior than mine. Of course, we have to find the coordinates. And it says of the y-intercept, but I'm going to go ahead and find the x-intercept as well. So for our y-int, of course, we let x equal to 0. Let x equal to 0. I get f of 0 equals to e to the power of 1 minus 2. And that's really it. You don't need to go further ahead unless using a calculator. We can leave it there. So our y-intercept is going to be at 0 e minus 2. To find an x-intercept, we go let y equals 0, of course, and we end up with e to the power of x plus 1 minus 2 equals 0, plus 2 on both sides. I get e to the power of x plus 1 equals to 2. I'm going too quickly. Okay, and then of course I'm applying my log. Right? I'm rearranging. I'm hoping we remember this step. If not, I definitely recommend going back to revise it. Log base e of 2 equals to x plus 1. How can I rewrite log base e?
ln.
Good. What does ln stand for? natural log, which obviously NL was probably taken or something. So we're using ln. It implies it's a base of e. We can just write ln of 2 equals to x plus 1. I'm going to rearrange that to just minus 1 on both sides. And I get, here we go, x equals to ln of 2 minus 1. So of course that coordinate right there is going to end up being ln of 2 minus 1, 0. Again, non-calculator, you're not expected to know exactly where the values are. This will suffice. Any questions? Okay. Later on, there are questions in the exercise regarding finding the equation of the exponential function based on a graph or specified coordinates. It works the same way. For example, substitute your points, find derivative, etc. We don't do a derivative of this one yet. We'll do that later on. Any questions? Okay.